before. It sounds like Leonid has something interesting to tell us. Maybe we should start there.
Actually, just before Leonid goes, I was supposed to deliver some talking points which we put together collaboratively. I'll start with Leonid's, which was he basically suggested that we consider untethering from Earth completely. Many of the concepts for space involve anchoring to ulnar, but who needs to anchor to from ulnar? You go to space, you don't have to worry about the weather. You go to terahertz. So that was one of them. Another, Vincent Fish came up with very much a discussion of the trade study between high orbits, which give you high angular resolution but slower UV coverage filling, and low Earth orbits that fill UV coverage very well but don't deliver angular resolutions very much in excess of angular resolutions available on Earth. Maybe I'll invite Shep to point to another talking point, since you seem very keen on them.
Sorry, you caught me a little bit off guard there.
Okay.
Well, I think we had come up with a couple of them. One was the Earth, and the other one was the import of another frequency band. So
okay.
it would be quite interesting just to raise this issue that the ngEHT prototype receiver that Gopal's working on and that others have been thinking about is 230 and 345. And the question has come up whether we should include a lower frequency band for not only calibration, but also science and compatibility with other instruments.
An 86 gigahertz band. So I am not the chair of the session, but I was asked, and when we had AV problems, I pronounce your name Uli, is that?
Whaley.
Whaley. Whaley, you are the chair, and I will hand over to you, but I was asked to come up with 3 talking points for you to use, and those were the 3. In summary, go to space 100%, trade-off between LEO and MEO and HEO, high versus medium versus low Earth orbit, and Shep's suggestion that a receiver could be triple band instead of just dual 230, 345, 86, 230, 345.
And of course, you could combine them and consider the frequencies you could do in space, even fewer constraints.
Except for building the receivers, which is very complicated. But I've been doing a lot of talking, and I'll invite our very large group, the 91 people here, to.
Okay, why don't we try these things in roughly in the order that I heard them, and I'll try to move on to the various topics that were raised. In fact, if you really want to untether from Earth, maybe we can even discuss going into interplanetary questions, if you really want to go far, which I think would be interesting. But it sounds like we can start with Leonid.
If I may comment on the idea of going too far, well, frankly, I don't see the reason to do that. What's the advantage? And the farther you are, more difficult will be communication to Earth, even if you do not process data on Earth. But just dumping data back to us, unless you go there and live there, there is no reason for our tasks to go to interplanetary distances. And as shown,
there are 2 ways to get resolution. One is to high frequencies with shorter wavelengths, or you can stick to lower frequencies and go further away.
That's correct, yes, but still, don't forget that once you are in the gravitational field of Earth, you can essentially exploit it for rather efficient UV coverage. But if you are away, it will be a task for you to actively shuffle your telescopes for UV coverage, and that's extra spending of everything. I would not go there at least for now.
Understood. However, I don't know, you may all already know the latest announcement by Mr. Xi Jinping of China that they're going to build the fast array of 6 fast telescopes. So sensitivity will be less of an issue. We can go much further away at low frequencies even.
Well, if Mr. President would foot the bill for that, I am for, but otherwise, no.
Right.
Yeah, there's what it says, as imaging instrument, it will be very difficult. So
Absolutely. Yeah.
it's just a visibility tracking.
Yeah.
Yes. By the way, Leonard, I think I had something else in mind before I tracked you off track.
So
I thought John said you had something to say for this session that you wanted to share with us.
Yes. If you're in space, you need fuel to reorient yourself to look at a new target. You don't have the Earth to help you, and you don't have a motor-driven thing on Earth that you can use. So that would limit the useful lifetime of it. If you are going to go into space, you'd probably want to go to the L2 point so that you don't have times when your antenna is very far from the Earth, and that would slow down your communications, and it would also mean that we heard about needing high precision in knowing the location of your antenna, and that would be difficult.
Okay, I see Leonard's hand up. Leonard?
yeah, my comment, I dare to disagree with on both points. Concerning fuel, first of all, if you apply known smart strategy, you just use action wheels. And sometimes, yes, you will be in need to dump the accumulated momentum, but that's not a big deal. That is not real limitation for many, many years for in-orbit operations. That is known. As for L2, I really don't see the reason to go there with mission of our desire. Again, you need UV coverage. And if you are in L2, you are just frozen there, and the gravitational field is weak, and it doesn't allow you to exploit Dr. Kepler in full for UV coverage. And if you are close to Earth, at medium Earth orbit, say 10,000 kilometers, for example, below geostationary, you can beat two things at once. You are close enough below the geostationary, and UV coverage can be filled up efficiently. And that is actually demonstrated. I can give you a reference that works. It's not a major concern. Processing the data, wideband, that's an issue, but it's an issue anywhere. And therefore, again, there is no need to go to L2, which makes this even more difficult.
Now, since this discussion is going off to space here, and I do want to keep it a little bit tight, at least to our audience on Earth, and not get too technical. However, I did hear from, I don't think he's in our meeting, from Ante Tao, that China is considering not only building 6 fast telescopes with a square kilometer collecting area, but also building a constellation of VLBI space satellites that will solve everybody's problem, including UV coverage. Even though I don't actually know much information on it. If anybody does, now might be the time to enlighten us. Yes, Leonard?
Well, I think I'm aware of this idea. It's not a project yet, it's only concept, but this is for a low frequency. It's not, well, low frequency. It's centimeter and decimeter wavelengths. It's not about frequencies of concern for this meeting.
Okay, let's see. Are there other directions we want to go on space at this topic? Or, I mean, I'm happy to take a bit more, but I'd like to keep it relatively non-technical.
Well, yeah, Willie. So I think maybe the most pertinent question for this conference regarding space is how does the proposed capabilities of ngEHT circumscribe what the space VLBI case has to look like? Or put another way, there's a lot of ideas for why people talk about going to space. Which one of them can ngEHT achieve on the ground? And a good example would be this idea of rapid UV filling. You can rapidly UV fill by having satellites moving, or you can rapidly UV fill, in the ALMA model, just have many, many stations. And ngEHT might be able to achieve that. And so perhaps, if somebody has something to say about exactly where the boundary between ngEHT and space would have to live or could live, that would be very productive here.
I think Shep has his hand up. Shep.
Yeah, I think Avery said it very well, that you want to maximize the science that you can do from the Earth with the ngEHT. And I think there's a very good case to be made that nimble small dishes can rapidly fill in the UV plane for relatively modest cost. And that if you go to space, then you'd like to optimize the use of the longer baselines. I mean, they're not inventing long baselines, right? So you have to go to space to get those. So going to GEO or MEO, or maybe even L2 or the moon gives you something completely new. So if we split these things, and then also recognize that the space VLBI can leverage the increased capacity or the increased baselines of the ngEHT in the future, that has a nice narrative flow, which allows you to have the ngEHT and then space and optimize the science output.
Now, we had a beautiful image from Radio Astron compared with EHT, that I think demonstrates a bit what you showed, right? That one can there are places where you can fill things in.
Willie, I want to make sure we have a very short discussion session, and the other parallel sessions have a time to present their summary.
Indeed, let's
I think, well, if I may, I think some of us talked about this before. I'm not sure if ngEHT include Sophia type planned observatory. Well, if Sophia is too expensive, maybe you can consider this upcoming platform like airship, which is, I believe that pretty soon will become reality.
You mean on a plane?
Yes, Sophia.
Do interferometry with a dish on an airplane.
Yes. It's already there.
Indeed, I guess the upside is you can place it anywhere you want. Downside is that it's not nearly as far away as a GEO or lunar.
Well, so you can do 345 or 420 or 690, right? That's a perfect location to do 690. Sophia is very expensive. No, I would think that you want to do something like airship, like a blip type of thing. Well, that's something much cheaper than going into the space, right?
Indeed, even though my PhD advisor told me that it's dollars way less in space, so it's not quite that you can convert space dollars into dollars on the ground. But yes, thank you everyone for the input, and we should move a little bit forward on covering the other topics that were raised. I'm trying to remember. So Shep, you were nominated to present.
I'm sorry, I was nominated to present for which?
For the discussion. I'm trying to remember. Jonathan, you said that you had Shep was telling us something.
Let's have the moderators from the parallel session.
Shep provided as a discussion point the possibility of a third receiver band. simultaneous receiver band.
Jonathan,
Yeah.
I want to give Lindy some airtime here. I think Lindy is pointing us to the fact that we have limited time and there are 3 other parallel sessions yet to report.
Indeed,
indeed. I beg your pardon. Absolutely.
Okay, so
I mean, I'm not the chair of the session, so please hand off Wei-Li whenever you.
Okay, so let's move forward since we're already halfway through this session. So I guess these were the presentations from the technical group. Is there anyone who wants to report from the shadow discussion that I was not present at?
Yeah, so we can do it like that, or we can do it in the order of these numbered groups. I think there is a group focused on astrophysics before us.
Okay, then Sarah, do you want to lead the astrophysics?
Yes, I can do that. So I have our discussion points that I put in our channel. So the session was really focused on how important it is to have multi-wavelength and multi-messenger synergy with ngEHT to observe supermassive black holes. So there were talks on the horizon scale observational prospects of nearby AGN, and those rely on flux estimates for lower frequency from lower frequency monitoring and accretion properties constraints from multi-wavelength SED fitting. It was expected that about 10 sources could be reachable with ground space ngEHT, but that needs to be narrowed down with multi-wavelength information and long-term monitoring. There was also a lot of really nice comments on the need to understand jet formation and jet properties with high signal to noise and high cadence ngEHT imaging, and a strong connection with the multi-wavelength for all jet sources, and also for connecting to gravitational wave experiments like LISA that is upcoming, especially for supermassive black hole binaries and extreme mass ratio in spirals. There was also a nice talk about the S-stars in the galactic center observed in the near infrared that seem to be in a 2-disk configuration that may infer a low spin for Sagittarius A star and a low probability for a jet, which would inform, of course, EHT and ngEHT observations of Sag A star. So that seems to be the main things that were discussed. Obviously, the multi-wavelength and multi-messenger aspect is very important for all of these sources and something that needs to be taken into account in the ngEHT organization very early on. Are there any comments or?
Let's see, I don't see anybody raising their hands, but I don't actually have access to Slack. Anyone have see if this question is raised in Slack?
I'm curious, did you guys talk about, does the monitoring have to be simultaneous? You know, do these have to be tightly integrated campaigns, or what sort of temporal coordination is needed, especially with the lower frequency arrays?
So I think the main speakers were Jose and Venkatesh, also on this low frequency radio monitoring. So I think in the case for jet sources that are currently observed and important, you know, like 3C279, OJ287, then simultaneous or quasi-simultaneous observations are very important for this kind of simultaneous SED fitting. In the case of the sample program that Venkatesh presented, I think that is just current ongoing monitoring work prior to ngEHT kind of observations. So to narrow down the sample, maybe Venkatesh, if he's here, he can say a little bit more.
Sure, yeah. So the idea is that look into the sample more closely on sources, especially where we don't see significant synchrotron emission at even at 86 gigahertz or so. So we are trying to see if that there probably could be a thermal synchrotron emissions dominating at these frequencies, and in which cases it would be interesting to have go to, I mean, perhaps have both simultaneous observations at low frequencies of the synchrotron and the emission of the thermal synchrotron, and try to constrain the accretion properties based on the short time scale variability in terms of the orbital time scales, or also perhaps some of the gravitational time scales if possible. But the reason being that we believe some of these sources lack even any millimeter emission detection at 230 gigahertz. So this is not, I mean, at this phase, we are not looking at simultaneous observations with the ngEHT or EHT. It's a long shot, but this is something to get a better handle of on the source list.
Okay, we have Andre.
Yes, I wanted just to coming from jet directions. I think with the contrast to black hole science with the EHT is that when you're talking about jets and doing something for jets with the EHT or ngEHT, it often sounds a bit incremental. So one needs to look at the angles which will be uniquely addressed when you go to higher frequencies, because many of the tasks that we do or try to do with the EHT observations for jets could be done in reality with GMVA, in fact, and with lower frequencies. So some unique applications we all need to think about it, because that's that will make this science actually relevant and better presentable. Over.
Thank you. We'll take one more question on this group, and then we'll need to move on to the last one. Anyone?
Svetlana?
Yes, I have a question to Jose Luis and his excellent talk, and it may be some continuation what comments which Andrei did, that, for example, for the EHT 3C279 image, we have kind of a problem to determine where is the core of the source for this kind of core region, which is a little bit extended. Radio astronomy observations also shows this kind of extended structure. And it is interesting, is it possible to construct a spectral index map using EHT data and radio astronomy data for this region? I don't know, Jose Luis is here or not.
Yeah, Zelena, yes, thank you very much for, this is an excellent point, yes. For OJ27, we actually managed to get a spectral index map comparing to radio astronomy, EHT and GMVA. Of course, as you mentioned, the registration of the images is always an issue. Doing the phase referencing will be, extremely useful for the ngEHT. But nevertheless, it is still, possible when you have, clear components, very well identified and optically sync emission that you can use to cross-correlate the images. So in principle, I think that's feasible.
Yeah.
And I also wanted to comment about, the comment that Andrei mentioned before about incremental science. I think there is a turning point, which is when you can actually, connect the emission from the black hole and the jet. And we expect to see this in M87 soon. And that's really not incremental. I think this really provides us with a significant view of how the jets are really launched and the connection with the black hole. If we can do this for more sources than M87, I think that this could be extremely important.
Yes, I only meant that we need to put emphasis on this kind of science.
It is also for dilatation, if we can have more or less simultaneous data of EHT and longer wavelengths, and it is especially important for the core region in sense of measurement polarization of co-regions.
Exactly. Yes, and also, Michael, you mentioned before about the how close in time should be these observations. I think it depends on the science we want to make. If you want to study high energy connection with a jet, and then I think we need to have an array which is really, can be remotely can be observed remotely, and have very very versatile array that can be used in triggering mode and TOOs mode. In these cases, if you shoot 2 days later, then you are missing this. And also for the for X-ray binaries, we had some excellent talks by Alex and Rob. And in those cases, you would like to have something that when you have a significant flare in X-rays or some significant change in the source activity, we want to catch that really on the fly. And so having something that you can trigger offline and get on some observations will be extremely useful.
Okay, well, I'm afraid it's all exciting and sounds like this is great, but we do have only a few minutes left, and let's move on and let's hear from Maciej.
Okay, so we met to have 5 really nice talks. I think an interesting feature was that all the speakers were at late time, meaning it was between 8 p.m. and 4 a.m. for our speakers, which is impressive that they decided to stick around. And we had some interesting discussion. There were some very specific issues related to particular spacetimes, particular presentations, but we tried to abstract some more generic questions that could be maybe good to share with you, and we'll get some comments from the broader audience. So maybe I'll just read those bunch of bullet points, and then I would invite you to comment on those. So how to even get an exotic object such as a wormhole naked singularity? Is the fact that in case we don't have an astrophysical channel understood to produce a given solution, should we not care about these solutions so much? Should we only care about things that we know how to form in realistic astrophysical conditions? On the other hand, there may be a lot in astrophysics we don't understand, and there could be solutions that are correct from the point of view of fulfilling GR equations, just we don't happen to know how to get to them. So that would be one generic question. How well the presence or lack of the photon orbits for photon shell actually inform us about the space-time geometry? Is that actually, well, enough? This will not inform us about the intimate structure of the event horizon. Point number 3, background space-time versus actual observables of the ngEHT. Would GRMHD, is it possible that GRMHD could actually be indifferent to the geometry? So, we try to realistically model astrophysical flow in one space-time and another space-time, and it turns out that it doesn't care so much about space-time, but it cares about, well, magnetic fields, initial conditions of the matter. Do we know that? Should we do GRMHD in more space-times? Should we do GRMHD in every space-time that anybody ever came up with? Sounds difficult. So I was asked to deliver 3, but I'll give you one more related comment from the group. So how are there generic features that we really could really help us to distinguish some sets of objects? For instance, during these talks, during our session, one presentation was related to naked singularities, and in our talks, we often repeat that, well, naked singularities should lead to smaller shadows than the black hole shadow. Well, it turns out that this is not a general truth, you can also have a naked singularity that will produce the similar diameter of the shadow as the same mass black hole with the same mass. So do we really have like good handle of some real discriminants of the exotic objects? And well, should we invest time into finding such features? Okay, so this is this is just meant to excite some discussion.
Andres.
I once talked to a guy who was doing quantum gravity, and he told me that his theory would be different from Einstein's at the scales of several hundred gravitational radii. And I told him, well, we could do this, we could measure that. And he asked me how, and I said, well, bipolar outflows. And he said the phrase that I will ever remember for the rest of my life. He said, in my opinion, science ends with spherical symmetry. So what we're looking is that effects which are actually working in spherical symmetry. So we need to get astrophysical variables and constants as cleaned up and cleaned out as good as possible. So I'm not sure you could do it with the simulations. We can do something, but it's probably good measurements of everything else, and especially of the black hole mass of the objects which we study, and the black hole spins and everything that we can get from other means. Then we should do that, and then try to get to deciding on the sort of fundamental questions. So that's the approach that I would say should work.
Andrei, you are calling Kerr-metric heresy. I see.
Well, we don't know what heresy is.
John has his hand up.
Yes, just a brief comment on the naked singularities. They would, if you were interested in those, you would want to look for things with that are exceeding the maximal spin for not having a naked singularity. So that would be subsumed by just interest in measuring the spins of the AGN and the other black holes.
So this is what I think is this kind of effects. If you exceed some limit on the spin, if you exceed limits on the magnetic field which are coming out from the Kerr or from black holes, that's the type of experiments we want to do it, because if we try to get sort of a difference on the effect on the jet on some larger scales, it's going to become very difficult and very inconclusive. You want to identify the fundamental quantity which you can actually benchmark against the Kerr black hole or other type of compact objects, and then measure those benchmark quantities as accurately as possible. And that probably would get these things, will get us to fundamental solutions.
I think that's not the only signature of naked singularities, at least according to the talks earlier today. It could be the shape of the event horizon, the size of it, the shadow that is, and so forth. So there could be several things to distinguish naked singularities.
Well, if they are super spinars, maybe they would have really crazy Blandford-Znaik jets going on. I don't know. Did people try simulating that?
Well, the super spinners, you have to ask the question, what stops them from super spinning ever faster, right? Because black holes will tend to accrete angular momentum. So why don't they just keep spinning up and up and up?
You mean in DR or in an alternative theory?
My understanding is you can have a super spinner black hole in general relativity as long as it's formed super spinners. They're sort of like tachyons. It has to be formed with a naked singularity and super spinning, and then that's no problem. You just can't get from here to there. But if you start there, like primordially, then that's okay. I could be wrong with that. That's my understanding.
Okay, Michael.
Yeah, I think it's clear there's this sort of zoo of exotic solutions. Some of them are fun just for academic interests. Some of them are legitimate astrophysical possibilities. I think it would be really interesting for the group on shadows and these alternative theories to try to start thinking about how to categorize these. Like, what are the really interesting ones to test, and what are the ones that we're just doing for fun? It's just an interesting mathematical exercise. I think it's actually really hard to come to grips with, what the viable alternatives are. It'd be great if we could articulate that and really narrow our scope for what should be determining architecture.
Yeah, just to add up on that. So I think the problem with a number of theories is that the bridge from the solution to an observable for a number of theories does not exist as of yet. So just for the fact that a theory that it's a particular mathematical artifact of Einstein's equations does not mean that it will lead to an observable. For example, certain solutions were discussed where they violate a particular space-time symmetry. Now, if you violate a particular symmetry, you lose the photon sphere. If you lose a photon sphere, how will you observe it with the ngEHT or EHT for that matter? So I think a question for a theorist's conscience is that, are you willing to forego mathematical artifacts for astrophysical observables?
By the way, I think I just noticed the technological limitation of the way I set up my Zoom is that I only see hands being raised of somebody who has a video up. I just see if I click on the participant window, I'm just realizing that there are a few more hands up whom I didn't see. So I'm going to mangle the names. Yours start.
Svetlana, is your hand raised up?
Svetlana, Avery, and Razi have their hands up.
No, I have asked already my question, so that sorry, I forgot to.
Residual hands.
Yes, I did.
Maybe Avery.
I have a question, if that's allowed. Can I ask a question? Yeah, so actually that was very fascinating about this, maximum of the spin of the supermassive black hole. I was wondering, can we imagine a scenario that we have emerging supermassive black holes in which because of the angular momentum export from one to the other, actually the export of the angular momentum to the first one would be quicker than basically the time that their mass is added together. So, I feel like that, is this visible what I'm talking about? I mean, imagine that you have two bars of supermassive black hole that are spinning very fast. And then it could well be that the transport of angular momentum from one to the other to the central one would be more rapid than just the time that takes for the system to completely accrete the less massive black hole into that. So in this scenario, you would end up with having the main progenitor, which is a slight reaction that has a slightly more spin. And imagine that was before extremal, so now it's actually above the extremal, but a little bit afterward with the time delay, its mass would be actually up such that the spin would be proportional to the mass or below. Is this possible at all, or is this just not that so possible?
So it's a very timely and obviously a good question, since neutron stars probably do such things, but we did get a Nobel Prize, I think, last year to Mr. Penrose, I guess, for the citation that he showed this does not happen. So not that I have read his papers, but that certainly is what the Nobel Committee credits him for showing that this did not happen.
Well, it doesn't mean that it doesn't happen or it cannot happen. Can we imagine a real scenario that it could happen, or there is some rules against that?
I think that's what I understood is basically his Nobel Prize, is that it cannot happen. Maybe somebody
yeah, you can do out the calculations in GR for the Kerr solution, and it's impossible to go above maximal spin if you're starting below. Even if you're merging or you're accreting, it doesn't matter. So these super spinner Kerr solutions, they have to start super spinning. So they're primordial or something like that. You can't get there through other processes that we know of.
Okay.
So Avery had his hands up for a while. But Avery, maybe you should cut me off since we are running over or something, but you clearly have the next word.
Oh, we certainly are. So I'm happy to carry this on later. I was just going to I was going to note two things. The first is my colleagues who work on quantum gravity have, of course, chosen to work in a field with very little empirical input, and I think they might like it that way. So asking them exactly which tests to perform is perhaps asking the wrong crowd. Then the second is we simply don't have credible, viable alternatives to general relativity. There was an era when people were developing these, then they ruled them all out. And so now we have slightly, well, perhaps not even slightly, very exotic alternatives. And at this stage, I think it behooves us not necessarily to think only in terms of a handful of specific theories and what that might produce as a prediction, but perhaps more generally in terms of how do we assess the consistency of what we see with the predictions of general relativity. In other words, think of this as an attempted validation exercise, not really attempting to prove some alternative. And along those lines, one of the things that looms high in my concern list, which brings us back to this statement that Maciek had made about trying to ascertain whether or not the MHD simulations really look all that different in alternative theories, is that the astrophysics could very well respond to minimize the impact of a gravitational perturbation. You know, we see this repeatedly in physics. It even has a name. It's Le Chatelier's principle. Complex systems respond to perturbations to minimize their influence. And so that could happen. And I think that's one of the places where the kinds of examples that Maciek was talking about are absolutely critical to determining what the real systematic uncertainties are in the kinds of tests we're talking about. So not necessarily asking what is the subtle impact on a jet 1,000 gravitational radii away, but rather if we're looking at a non-Kerr spacetime and we imagine it is one of these super spinning spacetimes and we've measured the spin because we're looking at the emitting orbiting material doing something, is that spin measurement going to reveal that it's super spinning, or is it going to look like a normal Kerr solution to us? Right, so there is room for this in this maybe dialed back approach of validating general relativity, just trying to determine what our systematic uncertainties are. But that's all I wanted to say.
Thank you. Since we are far over time, perhaps we should continue this discussion in various sessions tomorrow. I mean, these are obviously very broad questions. You know, they are stimulated by specific sessions, but I think this is the whole purpose of the meeting, of course, to ask what can be measured, should be measured, and so on. And we will certainly have more opportunities to come back to the very basics of what is or isn't meant to be measured. So I think on this note, I'll propose that we convene. I believe this is the end of today. And is there anything from the LOC that we should know about?
No, just thank everyone for sticking around a little over time. Well, I think we will post recordings of especially the breakout sessions, so you can review the ones you didn't attend. It'll be a little more complicated for us